Let's move now to the dynamic range queries. What's a dynamic range queries? If we come back to the definition of the Wikipedia of a range query, it consists of pre-processing some input data into a data structure to efficiently answer any number of queries on any subset of the input. Here, I modified a little bit the definition. As a data structure, range queries consist of pre-processing some input data into a data structure to efficiently answer and update any number of queries on any subset of the input. Because a dynamic range query is not only answering some queries but also update. I can query the sum or the minimum or any type of other function as what we have seen in the static range queries. Sorry. If I query from left to right, it's okay. We have seen this, but here I can update. I can update just one element on of the set, or update range of elements from left to right, and I query another time. So here we have two types of queries: a querying the answer, the minimum or the sum between in a range, or I can update a range or update just one element on the set. Let's talk about the different techniques that we have used on the static range queries, and let's see if it works on the dynamic range queries. First, the naive approach. We have no pre-processing of the data. To answer one query or update range, I need a linear time complexity. So it's bad, as you see. What about the perfect sum array? Also, I need here a linear time in pre-processing, and I need a linear time to answer one query. We have seen this in the linear on the static range query. It's constant time because we have no updates. But here we have an update, so we have to reprocess all the data. To answer the new the query on the new array. So it's not constant time. To answer a single query, we need a linear time. Oh, and of course the space complexity is linear here. The dynamic programming approach, where we answer all the queries. Also, we have to pre-process all the data. In static range query, just we process just once. But here, if we update the original array, we have to recalculate or recompute all the answers. So it's bad, as you see here. It's very bad. The square root decomposition. I need to pre-process once the data in linear time. We have seen in the static range query where I need square root time complexity to answer when one query in the worst case, and space complexity is also square root space complexity. But here, at first reflection, I can think that I need to reprocess all the data of if I update the original array. In this technique, if I update the original array, so I need to recalculate the array of the blocks in linear time. But I've made a little research, and I have seen that we can update in square root big O square root time complexity. I don't know this technique, to be honest here, but I seen an article that it says that we can do it in we can update the original array or the data structure in square root decomposition technique in square root of n, and also to query in one single query in the square root of n. I don't know this technique, so this is to discuss. The sparse table, as we know, the function must be idempotent. So here, same logic. We process once in n log n, and in static range query, we just need the constant time to answer one query. But here we have, if I update the original array, I need to reprocess to recompute all the data. So n log n. I don't know if there's a technique to optimize this or a way. I don't know. We have seen also the segment tree. The segment tree in a static range query, we have to pre-process in linear time, where m is the number of nodes on the tree. And to answer one query, we need this logarithmic log m, and the space complexity is linear also. If I update the original array, I can update the segment tree in the same time complexity here, which means log m. So it's very cool here. It's very great. If I update the array and or the segment tree and query, update and query, all this in log m, the same as the static range query. We will see also the Fenwick tree, called also binary indexed tree. We have to pre-process the tree in linear time, updating and querying in log n, and we need a linear time and of size n for the space to build this Fenwick tree, where n is the number of the size of the original tree, n is the size of the original array. So, as we have seen in this presentation, we have what we call a point update. A point update is just update one element, update one element in the original array. So we will to see the dynamic range query with point update. As usual, we're going to use this problem, dynamic range sum queries. Given an array of n integers, your task is to process q queries of the following types. We have two types, as you see. Type 1 is update the value at position K to U, and type 2, we have to compute the sum of values in range AB inclusive. Of course, you know the rest of the problem here. As input, we have here the size of the array, the number of queries, the elements, and here the queries. 2, which means arrange a query. 1, it means a point update. Let's understand the problem. Let's take this example. An array of size 20. We have just two queries here. These are the types of the queries: an update and the sum query. For example, if I have 2 to 6, which means we have a query, sum query, from 2 to 6. Sum of 1 to 5, because 1 to 5, because the problem and the indices are one index. So we have here to subtract 1 from the indices. Sum of 1 to 5 is 3 plus 1 plus 5 plus 22 plus 10 is this range. Okay. Now the second query is of type 1, which means at index 3 we're going to change the value from the value at index 3 to 10, which means from 2, because here, to 10. You see here in the presentation. So the number of queries is 3 and 2, because we have 3 queries. This one, and this one. 2 to 6, the same as the query number 1, which means the sum now from 1 to 5, it will be changed, because we have changed, we have updated this value from -1 to 10. So it will be 3 plus 10 plus 5 plus 22 to 10. From 1 to 10, so 1 to 5. This one. Okay. Now, after understanding the problem, let's see how to update the segment tree if I update an element in the original array. First, I need to calculate. First, I need to know the first index and the last index and the whole array here from 0 to 5, and I look for the middle. The middle is here. 0 plus 5 over 2 is equal to 2. Okay. Now we have to check if 3, the index 3 here, lies to which side, the left side or the right side. As you see here, the middle is 2, so we have two sides from 0 to 2, the left one, and the right side from 3 to 5. As you see, 3 lies to 3 to 5, so we go to the right side, the right subtree, if you. Now I have to calculate the middle of 3 and 5, which is 4. Now I have to check 3 lies to what side? 3 to 4, 3 4 or 5 5. 3 lies to 3 4. so I go left. 3 lies to 3, 4, so I go left. Now I need to calculate the middle of 3 and 4, this range, which is 3. So I need to check or to know which side I will go, to 3, 3 or 4, 4. You know, of course, 3 lies to 3, 3, so I go left. Here, as you see, I have the same index. Start and end are equal, which is 3 here. So at this time, I will update that node at position 9 on the segment tree. If guys you don't know what I am talking about here, all this technique or the segment, these techniques or the segment tree, you can come back to all my previous videos to understand all the techniques that we have shown in the previous slides, or how to work and how to build or to work with the segment tree. We have used this in the static range queries. So here I will update the node 9 in the segment tree from 5, let me see, from 5 to 1, because in the vision array I want to update A3 by 1. Okay, now I need to come back to the parents, come back on this path and update all the nodes in between. So here 1 plus 2 is equal to 3, and come back to the previous node. 3 plus minus 10 is equal to minus 7, and come back to the root, of course. Minus 7 plus 24 is equal to 16. This is how to update a node in the segment tree, because I just update just one cell, one element in the array. It's not a range update, it's a point update. Okay. The pseudocode, let's see together. I need a function that takes as parameters the segment tree, the start position and the end position, start at the end of the interval of the node, the position of the node on the tree, the index where I will update in the array, and the value, of course. As we have seen in the previous animation presentation, if start is equal to end, I will update that position on the segment tree both to equal to while, and I terminate the call of the function, of the current call of the function. Then I will calculate the middle. Then I will check if the index of the original array where I will update in the original array lies to the left subtree, which means from start to the middle. I will call that function from start to the middle, and I will change, of course, the position. I will take the position of the left child. The same index and the same value remains. Otherwise, if it don't lie, which means I will go to the right side. To the right side, which means middle plus 1 to the end, and this is the index of the right child, and the rest of life. After calling all the function, if we have terminate the left side and right side, then we will calculate the value, the new value at the parent. We need plus here because we want the sum. If we need the minimum, we can call the function min. Let's try to code to solve the given problem. Here are the input, all the inputs of the problem. As you see here, we have three in the list of the queries. We have the three variables, the type of the query, A and B. Let's split this. Let's say if operation op is equal to 1, I think it's an update. Okay, let's make a function, call it point update. It will take as parameter the segment tree, the start position, which is from 0 to n minus 1, which with n is the size of the original array, and as the position of the root of the segment tree is at first at 0, and okay, A subtract 1 from A because the problem is 1 indexed, and B is the value. Okay. If is not an update, otherwise else, okay, say else because you have 1 and 2 here, else I will display the answer of the query function. It will give me the sum from A to B. I will give the same parameters here. This one, position 0. Here we'll give the left side and the right side, which is A and B minus 1. Now let's build the segment tree. Is equal the new long is not n here, we call it n, the size of segment, the new size of the tree. With let's first compute k, which is I think the seal of log 2 of n, and m now is equal to 2 times 2 power k minus 1. If you forget all this stuff guys, you can come back to the previous video where I speak about the building and the querying and the segment tree. Okay, I hope I didn't forget nothing here. Of course, here I have to initialize all the segment tree to 0, all the elements or the nodes. I will use an array here to build the segment tree, not just pointers. Okay, because we want the sum. I need the function build here. It will take as parameter the segment tree and the start position and the end position, the position of the node, the current node. I think it's okay, and also the original array. Here I must give the original array A. Okay. As we know, if we have a leaf, then that node at position pos is equal to the A of the position. Okay, and terminate the current function of that code. Now we compute middle. We go left. I forget A here. Okay, S min, and the position of the left child. Same for the right side. Here we have 2. The right side. Okay. This is the end enter. When the left side and the right side are done, we compute their sum. Okay. I think it's okay to build the segment tree. Let's call it here, but before I forget, let's build my segment tree. Array A. The start position 0. Here I -1. I will take the whole array, and then I split the array by 2 every time. I call the function. Then the initial position of the root. The root is at position 0, the root, and I think it's okay for the parameters here. Okay. Let's query. Query will return an integer. Query will take as parameter the segment tree. Okay. The position, or the interval of that node in the segment tree. The left boundary and the right boundary, and let's make it here, and the position of the current node. Let's call it P. Okay. If we have no overlap, as we have seen in the previous part of the previous section and the static range query, if we have no overlap, which means if start is greater than right, I think, or let's come back to the presentation here and see the overlaps. Overlap here. As we see here, no overlap, which means the left and the right boundary and the range are completely outside the interval of that node, which means we have if the left boundary is greater than the end, or the right boundary is less than the start. Here or here, we can here or here. The total overlap, and in this case, the total overlap in this case. Okay. Let's come back to the code. Sorry guys, I forget a lot here. Which means the left boundary is greater than the end, or the right boundary is less than the start. Then here we have to return 0 because we talk about the sum. If we have a total overlap, left and start. Okay, S and right is greater or equal to the end. We have to return that current node, that element at that node. Otherwise, we have a partial overlap. We go left and go left or right. We compute the middle here. And we have to return the sum between the left subtree and the right subtree. Here is middle and the position of the left child, and here the left boundary and the right boundary remain the same. They do not change. This is the left side. Then now the right side of the segment tree plus 1 here, and here 2. Okay. This is about how to query. I think it would have the same parameters here. Start and position of the node, left boundary, right boundary. Okay. Let's take now the function point updates. It will take us parameters. Of course, the segment tree. We will update the segment tree based on the updated information of the original array. Start position and position of the interval of node, the position of the node, and the index of the array where we will update the value, and the value itself will be long. Okay. If we reach the leaf, which means, as we have seen here, we will compute the middle. If I reach a leaf, which means I will update that node, as we have seen here, from 5 to 1. So the segment tree at that position, or the position or the index and the node in the segment tree, which is P, is equal to the value, that value. And I will return to compute to the previous function, to the previous call of the function, in order to compute the sum of the parent, if all the 2 calls are terminated. The 2 calls are here. First, I have to compute the middle, as usual. I see it here. Okay. Now we have to check if that index I lies to the interval, to the left side, which means I is less or greater or equal to S, and I is less or equal to the middle. Now we're going to update. We call the same function, but here on the left side. Okay, left side s to mid, left child 2 over 2 times p plus 1, and the index and the value remain the same. Otherwise, if the index don't lies to that, or doesn't lies to the left side, which it means it lies to the right side. Okay, and we have to. And if the both calls are terminated, so we have to compute the sum between the left subtree and the right subtree. This is a point update in the segment tree. Let's check together if all is correct. So let's here first delete the pointer of the segment tree. I think will be many errors here, of course, as usual. Okay, 2 times power, which means power here. Cannot declare pointer to long int. Long int is it? Long A, and then 14. I think we have long A. Cannot declare pointer to long int. I think it's the error, I don't know. Okay. Yes, returns here. Is not pause, is the P. Same here, and the query, I think, here. P. Okay, I have to here. It's carrier return here. I think it's okay. Let's submit and try and see what. It's the name of the file here. Dynamic and sample. Okay. Dynamic versus I'm creating this one. The summary. Okay, as you see, the code is accepted because its time complexity to for updating or querying is like M, where M is the size of all the nodes, or all the nodes in the segment tree. And this is the function or the code of the function of the point update in the segment tree. You can practice the same problem or try to to practice in this problem, dynamic range minimum queries. Let's arm a queue with the point update, which means range minimum queries with point update. Same concept. Instead, the sum will compute the minimum.